today is on tensor networks. And thank you very much for inviting me. I appreciate being here. So tensor networks. Tensor networks are a mathematical concept that generalizes multilinear maps. And these networks have arisen in several different, actually independent areas of science. So one area of science that we're more familiar with tensor networks in for people in this room is quantum mechanics. At the same time, tensor networks have independently arisen in computer science. They've independently arisen in various different areas where they're dealing with processes that are linear, that have a composition law. So today I'm going to give kind of an overview, and I'm going to finish up with some current topics about the research that's being conducted related to tensor networks. And as you would have heard, if you study quantum mechanics, and many of you have, you would have seen quantum circuits. Okay? So as you will see today, that quantum circuits have a very close relationship with tensor networks. And so your skills from quantum circuits will be able to make you understand tensor networks much faster, and vice versa. The approach taken in quantum mechanics is to use tensor networks to represent quantum states, quantum operators, channels, etc. And we're going to go through, and I'm just going to kind of show you the basic idea, then I'm going to go through the formalities of this. So tensor networks is kind of like hieroglyphics. All right, it gives a picture, and you can reason with that picture, and it's a formal system. So independently of the work in quantum mechanics, almost independently, Roger Penrose came up with some ideas. The original tensor networks actually date back to the 1800s by Cayley, and he came up with these diagrams to represent algebraic invariance, which is a whole other discussion. Related to tensor networks is a Feynman diagram. Okay, these correspond quite closely in some sense, and more in modern times, in the 1960s, Roger Penrose came up with some graphical language to describe relativity and quantum mechanics. The mathematicians took it from there. They formalized it. Actually, several different areas took it from there. Inside of Oxford, where quantum computing was essentially invented, David Deutsch connected the idea of a unitary map as a diagram in a quantum circuit. Okay, independently to that, at the same time, there was work that was being conducted in the early 1980s, in the late 70s, by Richard Feynman at Caltech, and by several people, including Toffoli, okay, who the gate's named after, at MIT, where they were using different wire diagrams to represent reversible and quantum processes. So all of these different ideas, plus many more that I have not mentioned, come together today in what we now call tensor network methods, for lack of a more general kind of description. And as I do this, I'm going to follow my notes, and I have to rip the pages off because they don't really like to fold for some reason. So just, you know, it doesn't mean it's bad reading. So this is a vector. That's how we draw a vector. You think of this as a wire with a label. That label will take values that are subsets of natural numbers. So for example, 0 and 1. When I assign 0 or 1, so if I was going to write this, this will correspond as a vector. In Dirac notation, we will typically write that as a ket, and we will think of this as a label of a Hilbert space, depending on how we're doing things. But just for now, we will just write it as an index. That's a vector. Now, a matrix will be written like that. Okay? Now, I will index an array of matrices by adding let's say I'll write it as a gamma I, j, k. Now you can think of this as, for example, if it's hard to write this down. I can write this down in many different ways. Okay, there's different reshapes, and we'll kind of get to that in just a second. So these two things we're quite familiar with. This thing we're maybe not as familiar with. This thing will give you the reason why we start to draw these as pictures and why we interchange between abstract index notation and tensor networks. Now, going a little bit further, and I'll come back to this and I'll put it all together. This is called tensor networks in a nutshell. The cover, you'll never forget the cover. It's a nut with a tensor network in it. Okay, so you can find this on the internet. It's quite fun. The point of it is to basically teach people tensor networks. So I'm kind of following that. And in the tensor network notation, this will be equal to this. So on the wire, I'm going to be able to deform things by moving the boxes. Boxes will slide on wires, unless they go around corners. Then we'll get to that in just a second. Now, mathematically, how would you write this? This is called juxtaposition in English. This is the composition of two things in the plane. And what we'll do mathematically is we'll use the tensor symbol. Okay? So people should be familiar with this. This is maybe something that is not covered in beginning linear algebra. It's one of the pieces of quantum mechanics where oftentimes in quantum mechanics people are seeing that for the first time. It's a strange linear operator. Everyone's complaining about it, and you have to prove all this stuff. But I will say that this A is an operator, and I will say that that wire is an identity, and I'll say that A tensor identity, that's how I write my identities. Tensor identity. Okay, and you can work this out, A cross B. Now, going further, I have composed tensors by placing them next to each other on across the plane. I haven't hooked anything together yet, right? Okay, so what happens when I connect wires? This is a good question. Okay? It's kind of a beautiful thing if you think about it. If this is the identity, well, what is the identity? The identity is like a delta function, right? So the wire connection becomes a sum. It's very beautiful. So if you want to sum two indices, you connect them. For example, how would I write the product of a vector with a matrix? Okay, so as an equation, okay, so in linear algebra I would write this, let's say like this, okay, without coordinates. Now, depending on how I think of this, I could add a sum in. I could sum over I and j for those some kind of defined ranges that we're taking values over. A, I, j, psi, j, one open index at the end. Those two things are supposed to match. Putting them up and down doesn't matter so much. This is not, in terms of relativity, you will have a metric tensor. And actually, the word tensor in relativity will refer to objects that transform either with covariantly or contravariantly. In the case of quantum mechanics, depending on what you want to do, this may or may not be true, but that's not what we say when we say tensors. When we say tensors in quantum mechanics, these are indexed arrays of numbers. Okay, so it's a little bit different. Now, this is all very basic, and we continue. During my talks, one of the reasons why they're such terrible talks is because people ask questions and I get super distracted. But today you will ask questions because it's part of the process of speaking when you get stuck, because everyone should be able to understand this. You're MIPT students, smartest people, so ask questions and I will answer concisely and not get distracted. So
because mix it two different products. There should be usual product.
Oh.
No.
Yes, yes. So one of the most important things about speaking in public is you should make tons of mistakes and then blame your audience, especially if it's something really stupid. Okay, so guys, why didn't you catch that? What are you thinking? Okay, it's never the speaker's fault. Remember that. This is the most important lesson. Okay, so, and then you can start to make different shapes. So A prime, this will become reducible to just some matrix. You already start to see that there will become structure inside of your diagrams, and you can start to think about your equations interchangeably with the diagrams, provided, and this thing has been generalized to death by mathematicians, et cetera, category theorists have worked on this. There's people in England that have worked on this in category theory. There's people in tensor networks that have worked on it from various different quantum mechanics perspectives. And all of these things start to make great sense when you look at diagrams that are increasingly complex. In which case, writing down the equation will give you almost no real insight into it, where drawing the picture lets you see some structure behind your equation. And so that's the point. And it's not always the best way to do it. It doesn't scale very well. You can't draw a diagram that's massive, but sometimes you can get a good feeling for small stuff. And most of your education has been about solving toy problems, right? Most of my career has been about the same thing. Maybe the toy problems become a little bit more difficult, but it's all the same. So for toy problems, you can simplify stuff quite often. Now, what about a basis? Okay, every time, is anybody a mathematician in here? Okay, so it's an easy audience. So I like mathematics, but sometimes you get really irritated when you start to talk about only the foundations of the topic. So in my talks, I pick a basis, which means that the space, the vector space that we'll work in, and the dual spaces become isomorphic. There's a bijection between them. With respect to that basis, we call the basis the computational basis. It makes everything very simple. We could do everything without picking a basis, and it would make it a little bit harder, and it would still look exactly the same. Anyway, so typically in quantum mechanics, we will interpret. So I could interpret this. This is called abstract index notation. You can look this up on the internet. Roger Penrose used to use this. In quantum mechanics, what we think of for these is we'll typically think of, let's say, I, J, K, and we'll sum over it. Okay? And that's just a matter of interpretation, how you work with that. That's how we typically will deal with that in quantum physics. So going forward a little bit, we will begin to discuss now. And are there any questions so far? Yes, please.
I'm really sorry, I didn't quite get what does a matrix array do?
An array of matrices.
Yeah.
So let's say, for example, that my friend over here has 3 matrices. He's not even my friend. He's like, I hate your talk, but that's okay. I wasn't pointing at him. So let's say he has 3 matrices. Number 1, number 2, and number 3. Okay? So matrix number 1, M1. Matrix number 2, matrix number 3. Okay? Now I want to be able to select those matrices. So I draw each one of these. Okay, so I'm going to draw this as this kind of like crazy thing here. Okay, it's I'm trying to draw it like as 3D. Then what I'm going to do is I'm going to just stick, let's say I just stick this projector here, then a projector here, and then a projector onto this one. 1, 2, 3. We think it's orthogonal. So inside of my tensor, all I'm seeing on the outside is this. I put in A. A is 1, 2, or 3, and it'll pick those tensors. It's kind of cool, right? This is either super obvious or... Okay, so for example, if I have an array of matrices, I can index those with that third leg. That's it. This thing right here I've never drawn before. This is another problem with my talks, because I start to think, oh, it's cheating if I don't try to improvise, but that's not good. This is not comedy. Okay, so, which by the way, it is probably, probably time to move on. So It's okay. Now, I'm going to draw a C0 gate. How many people have seen this before? All right, great. Okay, now I'm going to do something super weird, okay? I'm going to draw a little pair of scissors, like this. I'm going to chop it in half, okay? Now I'm going to take this top piece like this, and the bottom piece like that. It's legal, they're tensors, they're linear maps, right? They're multilinear maps. It's totally legal. It's totally legal. Totally, completely legal. This guy right here, if this is A and that's a basis state, this one down here, this copies the basis of the the basis that is the Hadamard transform of this one. So I can have plus or minus. Etc. These two things, depending on what your normalization is, whoops. Okay, so those are how those things are. Is anyone like personally offended right now that I did that to the C0 gate? So for me, this like blew my mind when I thought of like, oh my goodness, it's actually a C0 gate. Oh yeah, we can just chop it in half. So this is really cool. This is like awesome. Okay. Now I'm going to show you how every quantum circuit can be evaluated as a tensor contraction. And to do that, let's use the quantum circuit that everyone is familiar with, because you're taking courses on quantum cryptography, courses on quantum computing, etc. And all I'm going to do, I'll put an H gate here. Now, by the way, H, of course, is equal to 1 over root 2 sigma z plus sigma x. Okay. The connection between circuits and tensor networks is very, very important. After all, this is just something you're drawing on the page. The connection to the physics is something that you put additional rules on, okay? Doesn't necessarily have to be, right? That's an additional interpretation. So to evaluate this as a tensor contraction, I can start off, okay? I'll start off in state, let's say state A, state B. Now, instead of drawing the measurements, I'll draw my measurements like this. It's a little bit nicer, right? So those are the measurements, states and costates. Now, this will correspond to some kind of tensor contraction. If first I will do it with, first I'll do this with open legs just to kind of show you. So I, J, K, L, M, N. So H, say I, J, then I'll have this dot thing, whatever that is, J, K, L, then I'll have this thing, L, M, and then you sum over that. So every circuit, this thing will have 4 open wires, and every quantum circuit can be interpreted as a tensor network by summing over the internal wires and leaving the external wires. So you'll notice that the first thing you're going to notice is you're going to say, well, isn't this kind of like path integrals in finite dimensions? And the answer is yes. So for example, if you will be familiar with this type of scenario, if I have A, I have B, okay, in the tensor network language, I can say that this is resolution of the identity is I. I'll put a summation there. Okay, and then I can start to split this diagram up. That's really cool if you have some GPUs. So you know, you've heard about these guys trying to do quantum supremacy. What they do is they actually apply these identities in different pieces of their circuit. They farm it out. So Google recently said, oh, we're going to get quantum supremacy with 50 qubits. Then these Chinese guys at Alibaba, like a couple weeks ago, they managed to break their circuits up a little bit differently, use some tricks. Then they simulated about 100 qubits with the same random circuits as Google. So it's kind of an ongoing battle, I suppose. Now, how is everything so far? It's very clear. Oh, sorry. Graphical. So I only know this because we have them now because someone gave them to us and my people like them in my group. So graphical processing unit. And so physicists take these things and instead of playing video games, they probably do that as well after hours. But instead of playing video games in principle, they're using them to make their code accelerated. And we have 4 of these in my lab. But the problem is you have to write the code for them. And Skulltech has 100 voltas. And they're getting more. So it's like one of the top 100 computers like around, so somehow quite big. Some people are probably more excited about that than others. Okay, so going forward, there are 2 paths to go forward. And I will skim over the next step. Number 1, this corresponds to what's called the XOR operation. So you want to be able to classify all the possible tensors you can make with XOR, okay, by hooking these together in any way you want. The second thing you want to do is you want to be able to understand all possible tensor contractions you can make with the connection of these 2 things. And then you want to think about how the Hadamard gates play into that. Then you start to realize, okay, these things are subclasses of the Clifford circuits, and you start to build this kind of hierarchy of different tensor structures. Okay, that type of stuff you can find in like reviews or surveys. The cool thing is that if you become familiar with just a few more of these rules, you can take everything you know about circuits and you can kind of upgrade it very fast and use these 2 ideas back and forth very fluidly. Now, the next part where it starts to get a little bit more fun is I start to bend wires. So this is the identity wire. What is this thing? And what is this thing? Okay, bending a wire. Okay, remember we picked a basis so there's not any funny stuff going on. This will raise or lower an index. It'll turn a bra to a ket or a ket to a bra. And that's pretty cool. It just kind of all fits together very, very nicely. So for example, I'm trying to think of a good example here. Okay, so exercises are very important. You should probably prove this. A transpose is equal to that. It's true, I promise. Now, interestingly enough, Sergey, all right, what if instead of putting this wire over here, I put it over here and I put this one over here, right? In this case, it doesn't matter, okay? Just like, for example, when I do this operation, I'll bend a wire, then bend it back. This just goes right to the identity, okay? So the types of tensors that we're working with, it's one of various different possibilities. So for example, if you worked with tensors that represented, anyons, world lines of anyons, or fermions, or something else, or you worked with stuff about general relativity, then they would have different graphical rules. We are just working with quantum circuits that kind of like patch together with this stuff. So, and here's another one that's kind of fun. So this one was by Roger Penrose. He just kind of, okay, so one of these I'll put a star on. I'll put a star to say one of them will be the dual of the other. Okay, typically people will keep track of everything going one way and all the wires going the other way, and they'll say that those are the duals of the other. So for today, we won't do that necessarily. Yes?
About this previous picture, is that definition of what is that bad line, or that line we should understand without anything and then just follow?
Okay, so that's a very good question. So let's say that this right here is delta ij, and let's say that this is delta kl. And then let's put like labels on this where these things match up, and you'll prove it yourself by just saying that those are delta functions. It's a very good question. So you can derive this. The mathematical thing is completely consistent. These guys are linear maps, okay? They're linear maps in the sense that you could think of this as a linear map from your Hilbert space back to itself. It acts as identity. This is a linear map from, let's say, some number to two Hilbert spaces, okay? This is the opposite of that. This is a map from two Hilbert spaces back to some number. So everything is a linear map, and all the stuff will work together. And that's one of the beauties of this stuff. People worked on it for a long, long time. And so for example, Sergey here is working on using these tools to study light matter interaction, qubits going down chains, et cetera. And he's using these tensor networks, and they're using it to really do kind of new things in physics. Other people are using these to study the correspondence between various different things, between quantum gravity and et cetera, et cetera. So spin networks, spin foams, all that stuff's closely related to kind of the mathematical formalism here. It's kind of the only thing we can do very well is linear algebra. So it's good to know this stuff. This is the trace. That's kind of cool. So you want to do a partial trace, you just trace it over. So this is a bra and a ket. I trace one over. Penrose, which I thought was really nice. So on a previous set of notes, I put this on the cover, and I credited it to him. He just took those and kind of moved them around. It's true. And you'll do that a lot. You'll actually do that identity quite a bit if you start messing around with channels a little bit. Now, going a little bit further, and I want to go through all of this in more detail. So at some point, if you found this stuff really cool, it's actually quite good because there's a lot of quantum mechanics and a lot of quantum information going on at MIPT. I think this graphical language is really quite handy. Here's another example of what you can do. So I'll start off, and by the way, as you notice, what I'm doing is what I'll do is I'll switch my notation multiple times throughout the talk, even for my own self. Everyone in physics is doing this because we kind of have managed to prove that it's okay to do that. For example, upper and lower indices don't really matter. Everything's okay. It's all about the interpretation as long as the connections make sense. And that's completely fine. We're able to do that. I'll put an H gate here, and the first thing will happen is I'll let this H act backwards. This will go to plus. Now over here I have this relationship, and I'm just drawing it that way to make it a little bit more entertaining. 0 XOR anything is anything, right? So this thing becomes the Bell state. So it's kind of cool. So you can reduce a bunch of different quantum circuits. A bunch of different quantum circuits identities will have various different interpretations. There's like loads of papers on it, and it's kind of fun to play around with. Now, here we'll have to start, so at the other side here. So here's kind of a nice one. I have a quantum state, psi, and I'm acting on it with some map, S. Okay. I'm going to flip that around and show that this is equivalent, by just applying these wire diagrams, of a deformed state given by that map acted on by a deformed map given by that state. And the way to do that is quite obvious. You just think about just kind of shifting these around. And then you kind of draw that one inside of this, and you put this one inside of a box. You can, of course, do this by applying the snake identities, this zigzag equation, and then unapplying it. It's kind of fun, right? But mathematically, this makes perfect sense. Are there questions about this? I think no. But if you have one, it's good. Super boring or super exciting, I don't know which. So that's kind of cool. Now, there's one little bit of confusion which is in the notes. The first thing that we want to do is if we can raise and lower indices and we're saying it's the same thing and everything's the same, then you say that the raising and lowering of indices and this identity will form an equivalency class on your space of tensors, and you can count that, and you can go through all of that stuff, and that's in the notes. Now we'll get to some stuff that's a little bit more fun and possibly more useful. Has anyone in here have any experience with matrix factorizations? So there's a singular value decomposition. This is quite a basic thing. If you didn't cover it in linear algebra in the first couple of years, you probably saw something quite similar to it. And so it's not too hard to deal with this. Okay, so the singular value decomposition says that for any matrix, it doesn't necessarily even have to be square. For any matrix, this can be factored into a unitary, a sigma, this U, V unitary, sigma is a non-negative diagonal. So that's kind of cool. It's not unique, but the degrees of freedom, actually, because this is diagonal, you can actually gauge transform it by diagonal complex numbers, okay, on either side. And they, as long as they're roots of unity each entry, then it's okay. So that's it's canonical up to that. There's one called the Penrose-Moore factorization, which is very similar, and that one is unique, but it comes with a little bit of extra overhead, and this one, for our purposes, is quite sufficient. Now, is in the graphical language, what I will say is that this map A will be able to be expressed as some U, some diagonal, and I'll draw these as diamonds, and some V. You can use this, and you can kind of, as we will see in a minute, we'll look at our Schmidt decomposition, and we'll kind of reference it back to this, and we'll see that they're essentially the same thing. Now, what is the point of the S?
Why is the form different in the middle? Why the sigma is
Oh, okay. So the way that you draw your tensors is just up to the interpretation of the person using them. So I personally prefer to draw that as a diamond, and the person who drew that as a diamond first that showed me was named Stephen Clark. Okay, so I learned a bunch of stuff about this from Stephen Clark, and Stephen would always draw his non-negative diagonal tensors as diamonds. I don't know why, I can ask Stephen. And I kept that convention. These are unitaries, and I just leave those as boxes. This is a non-negative diamond, and it just kind of helps you keep track of what's what as you go through. Some people will do it differently. Maybe they'll make it as a circle or maybe all squares and just label them. And that's okay. Whenever mathematicians have something and they don't know what to call it, there's a good chance they said it's a rank, right? Rank is everywhere. So in this case, rank, some people even say the rank of the tensor is the number of indices. I'll say it's order or valence. But rank, I will use rank, which I consider to be correct, at least in this scenario. Rank is the number of non-zero entries in this matrix. Those are called the singular values, okay? That's rank. Okay, now, And this is leading somewhere. This isn't just going something random. So the first question is this. What if I throw away some singular values? Okay, what do I mean by that? So if I take this sigma here, and I just toss out everything less than epsilon, okay? Then I will, okay, so if I have a matrix M is equal to, let's say, we'll call it U dagger sigma V. Now I'll say M twiddle is equal to U sigma twiddle. The difference between those two things is one of them I truncated, okay? The theorem by Eckert, Young, Mirsky. Is Mirsky a Russian name? It might be. So this was done in, I think, even in the 20s or 30s. Yeah, 1936. They proved that they first proved up to a Frobenius norm, but then they proved for any unitary invariant matrix norm that the best approximation of M that you can do for a given rank is as good as just tossing away the singular values with the SVD. So in other words, if I have two approximations, if I have M, let's call it M prime, and these both have the same rank, okay? This approximation is never worse than that one, this other one, under the unitary norm, which basically means, to summarize, because we're not mathematicians, if this stuff super excites you, please talk to me later, just kidding. No, if the mathematical part excites you, there is a lot of work in physics with math, but this is what it means. When you truncate your SVD, that's as good as you're going to get. Okay, that's the best approximation you're going to get for that given rank, And as you study, for example, you study a Bell pair. So 2 bits of information that are entangled, that shares 1 e-bit of information. Those things are perfectly entangled, okay? Now, what if I have a qubit, okay? If I have a qubit, what's the most entanglement you could have? Well, you think about the rank. If your rank is 3, you might be quite entangled. In principle, if your rank is 3, you have a different type of entanglement, depending on how you quantify this. I don't want to get into some kind of debate about entanglement measures, but if you have 3 singular values in your 2-qubit state, 2-qubit state, that, of course, is a different type of entanglement than if you only have 2 singular values. So in some sense, the idea of rank will order, okay, put some kind of partial order on the types of entanglement and the types of correlation that you have. And this idea of rank will be very, very crucial when we talk about how to use these tensor networks to simulate physical systems, to study different properties of various protocols, et cetera, and to do different matrix factorizations. As I continue, are there any questions? And I think I'm covering a lot of stuff here, but it's all very basic. But you can still ask, because it was probably harder for me than you to figure this stuff out. So. Okay. Using this, we're now going to go up to contemporary literature. You can go on the internet and you can be like, wow, I can almost read that paper now. That was maybe the worst lecture I ever had, but somehow it was effective. So here's what a tensor of a general state looks like. I, J, K, L, M. This corresponds to I, J, K, L, M. What is that? Does everybody agree with those two things are the same at this point in the lecture? Yes? Does everybody agree that I can always chop a matrix like this? Yes. So now all I'm going to do is I'm going to chop this thing up, and then I'm going to write it as what's called a matrix product state. Don't complain, because this is not how you're going to get it in practice. This is only a conceptual way to show you how to get that matrix product state. So for example, I'm going to chop it in half. Look, this right here, 1, 2, 3, however many that is, however many wires that is, okay, I group those into one big wire, and I have a bipartite split. So, put a diamond in the middle. I have some stuff out here. Then I just keep doing this until I can't do it anymore. Okay, and that's called a matrix product state. Why would you do that? You would never do it like this. This is only a proof, or a proof by construction, if you will, that any quantum state can be factored into this chain-like representation. So we'll apply it again over here. We'll chop. We'll have two wires here. Okay. You keep doing this, and what you'll see is, so we continue. Now I'm over here, and what I'll have is and then one of Sergey's students is like, but wait a minute, we don't leave those triangles in the middle of the wire. Okay, that's true. You don't need to leave those triangles in the middle of the wire. Some people will take the square root of those and multiply one to the left, one to the right. Other people will just move them all to the left. It doesn't really matter. It depends on your situation. And so you'll arrive at the final form, which looks like this. Okay. The first thing you should be asking, okay, so I think everybody follows this so far. And if so, this is the most, I'm not trying to brag, but if you actually got this, this is actually a very good lecture, because this is really hard stuff, actually. So let's continue our discussion of this, because this is almost like exciting and almost like kind of cool. Here's what's happening. Why is it called a matrix product state? Yeah? Remember before when we said, why is this indexing a bunch of different matrices? Do you remember the question? It was a very, very good question. A very good question. Okay. This open wire corresponds to what they'll call the spin index. What does a spin index take? For example, it could take a finite number of values, 0 and 1. Maybe you're used to dealing with +1 and -1, but typically in quantum computing, they'll say 0 and 1. This open index can be evaluated at 0 and 1. This internal index is called the bond. It's called the internal bond. This has a specific rank. Now, in this particular case here, we chop this in half, which means, okay, if these are qubits, somehow that chop scales as 2 to the n over 2. Okay, scales very poorly. You have to put the entire thing into the computer, do the SVD. It's very difficult. But what if I were to tell you that there are algorithms called tensor network algorithms where you can fix this bond dimension and you can find this matrix product state to represent different things of interest. For example, the ground state of a many-body system or the simulation of a quantum circuit. That is the point of this. Let us continue. Now I'm going to label these 1, 2, 3, 4, 5, and I will return to my labeling I, J, K, L. And remember, this right here is a map from one wire to one wire. These are maps with 3 wires. Okay, but nonetheless, I will write these all as A1, A2, A3, A4, A5, and then I'll just put an index on it, I, J, K, L, M. Some people will write the trace here, That just means it's some kind of trace. It's a tensor trace, if you will. It just means that you're closing this network off. Then I'll put my basis I, J, K, L, M, and I'll sum over those. You'll notice, if I put in values for this, let's say I put in all zeros. All zeros. What does it mean? What does it mean if I put in all zeros? That means I put a 0 here, a 0 here, a 0 here, a 0 here. Now look, push those inside of it, a product of matrices. That's why I call it the matrix product state. So it's really cool. Now, let's give some examples of it. Are there questions about this? So right now, we've only showed how to get it, how to basically understand this kind of strange notation. This is really in papers. I don't really like that notation, but this is kind of, I can't think of really a better way to do it either. So that's life. Okay, so this is a tensor diagram for some kind of general qubit state. This is a Dirac notation for some general state in a basis. These two things we agree are equal. This thing, I chop, I apply the SVD, and I factorize. Now I relabel the tensors, and I write the same thing like this. And it's showing that this quantum state can be rewritten as this product of matrices, which is kind of interesting. It's a linear chain of matrices, and it's it becomes very, very interesting. So why is it interesting? Why is it interesting? So we deal with mean field all the time, right? What is mean field? Who wants the answer mean field? It's kind of a trick question because what mean field means depends on who you ask, actually. But mean field typically for people like us, this means that you have rank 1 solutions. What's a rank 1 solution? A rank 1 solution will look like that. What is a rank 2 solution to a problem? Let's say your ground state has rank 2. Okay? Rank 2 means that the internal bond has dimension 2. Now, let's assume that your system is periodic and translationally invariant. Magical thing there is, I only need to keep track of one tensor. They're all the same in that case, and that's what becomes very cool. So here's what I'm going to do. Okay? I'm going to write down a matrix. I'm going to put, let's say, psi1, psi2, psi3, psi4. I'm going to raise this to the power of k, and I'm going to trace it. And I'm going to forget about the normalization. Let me do a specific example of this, just as an exercise. Okay. So think about what can you do with these quantum states. Okay, before we show how to get them, we're just going to think, okay, this quantum state could actually be really quite complicated. You know, so this inside of it is another quantum state. I multiply all those matrices of those together, then I trace it. On the output, and remember, when you do this, depending on your system, okay, this particular system is translationally invariant, so you can you have this symmetry. You know, the symmetric group will commute with your representations, so I don't really have to keep track of where these things lie because the whole thing's symmetric. So this right here can represent a very complicated quantum state. What is the rank of that quantum state? Rank 2, right? Rank 2, maximum, rank 2. Okay? Many problems in physics have a simple solution of bounded rank. Those correspond in 1D to things that are called gapped Hamiltonians, which we will talk about right at the end. Going to this is a GHZ state. if I put a square here, that's a Bell state. I'm ignoring the normalization factors. This one I think is a W state. Okay? This is kind of fun. It's just a different way to think about what you already have. Now, if you're looking to write a program to do something, the reason why everyone was really excited about matrix product states in physics is because of the fact that this representation allowed them to solve new problems. And they had something called TEBD, which was invented by Vidal. There's a number of papers. In my paper, there's loads of references, so the parts that I didn't work on are well referenced from other people's work. I'm going to show you this algorithm, which is an imaginary time. It's called an imaginary time algorithm. When you evolve an equation in a long time limit, it'll drive that equation into its lowest eigenvector. Right? For example, if I take a to the power of n, and I let it act on some vector, I take n to infinity, that'll go to one of its eigenvectors, and that'll be the dominant eigen. That'll correspond to the dominant eigenvalue. So that's what we'll do. And by the end of the day, by the end of actually the next 10 minutes, you'll understand TEBD. Then I will show you a couple of other things that are kind of fun and some pieces of the puzzle that I'm still working on, and then we will conclude. So here's what I will do. We have to pick our Hamiltonian that we want to simulate. We're going to pick a spin Hamiltonian. These things will work for infinite dimensional systems. Certain things will change, but not as much as you think. So what we will do is we'll say that our Hamiltonian H is equal to some, let's say I is less than J, and we'll say sigma I, J. These things are not defined. It doesn't really matter. And let's say plus summation over, let's say, sigma twiddle I. And we'll put an H in front of this. No, not an H, because I already used H. We'll put a J in front of it. OK, let's say that I really am interested in simulating this for some reason. And actually, we'll just put it on. Let's put it on a ring, just for fun. So what is this? You have a ring. Your Hamiltonian acts on everything, going around that ring in pairs. Then you have some kind of local term which doesn't commute with that. And I want to make my computer simulate that. How would I do that? Okay. One way to do it is to take this thing and to write it into Python and to diagonalize it. But that won't work very well. Right? It doesn't work. Because it's too big of a matrix. So I'm looking for, let's say, the ground state of this. I can evolve this equation by doing two things. I will take each one of these and I'll represent it as a unitary. And I'll take each one of these and I'll represent it as a unitary v. Okay? Then I will use what's called an integrator, which is called a Trotter-Suzuki approximation, which says e to the a plus b, and there's a whole family of these, times t is approximately equal to e to the a, e to the b, plus o t squared. Which means that I can take the exponential of this, and I can approximate it by a series of gates. I can make increasingly better and better approximations. There's references. This is a whole. You can actually derive these by yourself. They're not. Most of them are not that hard. Some really fancy tricks kind of got it started, and it's a cool area. Here's how this thing works.
You probably lost T.
Probably. Let me think where. Yes. So one of the most important things, and this is your fault, remember, is to always blame the audience. Okay. Here's what happens. This is super easy. What I do is I take my u, and I take my v, and I'll just sequence them. And then the v's will be little ones like this, etc. It goes on forever. Okay? That's just a big, long description of that circuit. So I can store actually a very long one of those in memory, or I can generate these as I go, which is the way it's actually done. And here's the trick. Here's the trick. This is a tensor network state with what rank? Rank 1. I cut this out, I remove it. This is equal now to what? Well, it's equal to this. It's a tensor network. Sorry. Okay. I take this, I do an SVD. These dots are now different. This triangle, I turncate. I throw away the small singular values. I repeat this process forever. That's the whole algorithm. It's pretty cool. Is it clear, Sergey? Sergey knows it. So this guy's an expert on this stuff, so you should ask him. I actually feel like, I'm like, hey, I'm giving a lecture to an expert. This is like kind of, makes me feel good. So let's think about this for a minute, because it's not, the matter of giving the presentation is not to like show people how hard this stuff is, but to just show it's actually possible to understand it, because this is used every day. There's papers on this every day, and if you understand it, you can almost read those papers. So you go through, you take and you push a gate on, you pop that tensor out, you do the SVD, you throw away the small singular values, you put it back. You go to the next one, then you chop it out. Now remember, eventually the thing starts to look like this. So when I push a gate on here, I chop this whole thing out. But remember, these two, it's fine. Right? Everybody sees that. Just pull a piece out, do the SVD, throw away the singular values. That's called TEBD. It's pretty cool. I think it's pretty cool. So we showed that the SVD was the truncation of the SVD is the best approximation that you can make. And in the notes, it shows that that approximation scales fairly well with the largest singular value that you throw away under the 2 norm. So that's another point of discussion. Continuing on. Okay, so if you study entanglement and you study entropy, there's a large discussion that you can go into from this stage of the game, okay? All about the rank, et cetera, et cetera. This is a very long, detailed discussion, which will be saved for a later date, or you can ask Sergey, et cetera. And continuing now, I will show one more thing just for fun to show the vast array of different possibilities. Remember digital circuits. So did everybody take digital circuits in freshman year? Like first year, maybe you saw this like and or gates in some one of your classes or something. You can think of those as tensors. So I could think of an and gate as a tensor. I could bend a wire around and think of this as a quantum state, where the bits of that quantum state could be the truth table of and, 0, 0, 0, plus 0, 1, 0, plus 1, 0, 0, plus 1, 1, 1, right? This is the logical and, so these two are anded, 1, 2, 3, 1, 2, 3. This is the and of those two, and you could do that, you could think of that. Then interestingly enough, you can extend a bunch of different ideas from satisfiability and computer science over to the tensor network language. People did a lot of that. And there's all kinds of tensor contractions representing different counting problems and combinatorial problems, which is quite cool. And some of those are even related to partition problems, which is all about counting things. And so that's kind of some cool stuff to Okay, so to kind of think about where we are today, okay, so how much time do I have left? Why are these lectures so long? It seems like I've been up here for an hour. Oh, I guess I'm right. No, I don't know why, but the lectures are super long, and I'm a very concise lecturer, so for me, this is like a lot. Okay, so one of the interesting things now, I have to go backwards now, okay? So you remember this Levi Civita symbol? Which every time I say that, I have a student named Vito Lile, and so it just turns into like this mess now. But the tensor networks, okay, so there's planar graph 3 colorings. So in 1971, Penrose said that if you take a planar graph and you replace it's a 3 regular planar graph. So every edge has 3 nodes, and you have some graph. Okay, etc. And it keeps going. If you want to know the different 3-edge colorings of that graph, you could track the tensor network. So there's a bunch of different stuff like that. The people in mathematics did a bunch of different stuff about that. It's kind of a cool result. And more recently, we are now concerned with how do you use a quantum computer to contract tensor networks and to do different things with tensor networks. It's kind of an obvious idea. So you think about, this is designed to simulate a quantum system. What if I had the quantum system? What would I do with it? Well, I would maybe use it to find tensor network states. It's kind of an easy, kind of a fun idea. If you want, we can go through that. If you don't, we can also leave right now. What do you think? I mean, I'm fine. I mean, this is.
Normal lecture, 1 hour and a half.
Okay. All right. We'll keep going. So we'll keep going. There's no getting out of this. Okay. So all right. Okay. So that approach has a name called split operator method. Split operator method. All they do is they break it into 2 pieces that commute with each other, but they don't commute together. So that's just yeah.
Why that's the networks then here? I mean,
Ah.
where do you physically see it, and what is so good?
So the reason the tensor networks are quite good is because it'll give you a bounded rank or a fixed rank solution to the simulation of that system. So, and interestingly enough, it is now proven that bounded or fixed rank solution will be a very good solution for certain ground states and also certain evolutions. And so the new ingredient here is basically to have that rank into the algorithm. And the other ingredient, which I think is quite nice, is it has a pretty evident connection to quantum computing, because you're dealing with unitary matrices and states, and so that's where kind of the next piece of the puzzle kind of fell in. So it's not the end all be all. I'm not one of those people that says tensor networks is going to do everything. It works very well in 1D. In 2D, it's a mess. Yeah. Yeah. In 2D, it's a mess, by the way. But still, everything is a mess in 2D. We don't have good 2D methods for simulating physics. That's just a fact. But in 1D, tensor networks works very well. So how would I make a tensor network? How would I make a matrix product state on a quantum computer? It's an interesting question. Here's how I would do it. I would start off so let's say, for example, that's 0 tensor n. Now I would come up, let's say I want to make a rank 1 tensor network, or rank 2, sorry. I put a gate here. That's a matrix product state. The pattern will continue. You can make higher rank ones by having this cross more wires at a time, etc. It's quite cool. What would I do with that on a quantum computer? What would I do? What are some algorithms that I'd want the quantum computer to do? So one algorithm is, let's say that I have a black box function, which is a unitary Q. And all I want to do is I want to find an eigenvector of Q. Okay? So Q promised Q is promised to be unitary. And what I want to do is I want to find a rank K approximation to some eigenvector of Q. I don't even care which one it is. Necessarily, because Q is promised to be unitary, I know that the spectrum of Q is distributed on the unit circle, right? That's all I know about Q. I know it's unitary, I know that. Now, here's what I will do. I will parameterize a quantum state with some vector of parameters theta. Theta will be entries of theta will be in 0 to 2 pi, let's say. This will be written as U dagger like that. Okay? So this is a trick where you take an expectation value of an observable on a quantum computer. It's well known and quite obvious, but you can use it to find fixed rank eigenvectors of Q. Now, I will write psi twiddle It's just it's given, but we don't know anything about it.
What we deal with it? Okay, some 2-qubit unitary matrix. Yes.
It could be a 100-qubit unitary matrix. Okay, so for example, you want me to give you an example to motivate the problem. Let's say like this. Let's say I have a quantum computer with a free Hamiltonian I do not know. Okay, and Q will be generated by the Hamiltonian I do not know. Okay, something like this. But you'll actually see that this type of problem can be used to solve many different things. But typically in quantum computing, we will make some kind of abstraction, solve a general problem, and then we'll look for like kind of specifics. So Q is just a unitary matrix, and it can correspond to many different things. Now, I will think of, and this is very, very easy. So right now, there's a certain type of trend in quantum computing. And here's how it works. What you do is you have a quantum computer, classical computer. Your quantum computer will be controlled by your classical computer. You will run your algorithm. You will get feedback. Then you will update everything and run it again. For example, you're trying to minimize a function. In this particular case, that's the exact trick that we're going to do. This is a standard kind of approach. They've done stuff like this in experimental physics for a number of years. At this point in quantum computer science, with the advent of these new chips from Google and from IBM, we're at the point where we want to be able to make these chips do something. And if they do anything, we congratulate ourselves. So these types of methods are heavily reliant on classical feedback and classical processing to use the quantum computer for as short amount of a time as possible and to optimize something as quick as possible. So that's kind of where those methods come from. Now, I will define pi of theta to be okay. Then I will use something which is standard in machine learning, which is I will create what's called an objective function or a fitness function, and I'll use log likelihood, and I'll say that the log likelihood of theta is equal to I equals 1 to n ln of pi. That's this thing. And the log likelihood function, when you minimize it, it corresponds to maximizing the probability of measuring each qubit in 0, which is exactly what we're trying to do. So what we're trying to do is this. Remember, if I have this equation, let's say this is lambda q okay, that happens if and only if it's an eigenvector. All I'm doing is I'm going to find a stationary point on that, so I'll minimize that log likelihood, which will maximize the probability and make the observable sharp. Okay? When it's sharp, that will correspond to the eigenvector, and that eigenvector has controllable rank. And so that is the purpose of this entire algorithm that I'm kind of talking about right now. There's a bunch of different sub-ingredients of this that kind of go into this, which are maybe not so, see, we're losing people at this point. I knew, that's the thing. You'll remember, you'll be like, didn't he try to get out of his lecture an hour and 5 minutes into it? You got to think. You got to think ahead. So where do we see this going? So why is this of interest? Why is it of any interest whatsoever? Let me tell you why it is, okay? First of all, Q, we will replace Q, like this gentleman said, with something more interesting. We'll replace it with some Hamiltonian we want to study or something else. But being able to do fixed rank approximations to problems of interest is quite different than how people are currently thinking about quantum computing. Okay? So it's actually very different. So for example, in the variational quantum eigensolver, they think about generating a quantum state and doing these expected values and getting out some kind of minimum energy for this type of physical system. But they have no theory for how to understand the types of states that they're preparing, in the sense that they don't have, they don't have an understanding of what type of rank they're actually producing with those states. Now, in addition, and this is something that I'm kind of continuing working on with those two gentlemen up there. So Mauro is from Chile. He's a Chilean gold medal physicist. He came to Moscow to hate life and to work with me and Tim. Tim was a really nice guy, and then he started to work with me. And so now he's a postdoc in our lab. And so we're working together to talk about quantum supremacy. And we're applying these tools from quantum supremacy or from tensor networks to talk about quantum supremacy. Now, my findings to date is very interesting. So so what is quantum supremacy? Quantum supremacy is when you have a quantum, this is how they define it. What they do is this. And it's quite cool. It's almost funny. So you take and you randomly put a circuit on you randomly hit it with a bunch of quantum gates. Then you have a classical computer over here. And when you can't simulate it, classically, you say quantum supremacy. My Google computer rules the day. Now, Google's been beating the quantum supremacy drum for a couple of years now, okay? And the interesting thing is, I don't want to give away too many of the details. The interesting thing is that some of their statements, although there's no theory in what they're doing, it's all numerics, which is fine. So quantum supremacy has to have numerics. Don't get me wrong. But there's implicit assumptions of how the physics of their chip behaves in terms of the area laws, being volumetric, et cetera, et cetera. Sergey's like, yeah, those guys are kind of chumps. I didn't say it. That was Sergey. Sergey's going after Google. Did you guys hear that? Just kidding. It's a joke. Okay. No, but the point is that what they're doing is they're simulating their self. It's like the Ouroboros of quantum supremacy. Then Alibaba just came in. It's like this ongoing saga, like Alibaba versus Google, right? Okay, Alibaba came in and they increased the size of the circuit that they can simulate. Okay, we're coming in and we're trying to do some lower bounds, and we're trying to basically put the entanglement theory back in, and we're trying to say, look, we don't want you to claim quantum supremacy and go to the New York Times. We want you to do these measurements, which will tell us how the correlations are decaying in your system, which will prove if your system can actually have that much entanglement. The underlying assumption of random circuits is that the amount of entanglement is very, very high. In other words, as people in the audience, and I won't use the name again because I've already brought him into this discussion more than I should have, and it's on video. Luckily, it's only an iPhone. This will disappear in 20 years, don't worry. The underlying assumption is, for random circuits, is that the entanglement is very, very high. It scales with the volume of the total number of spins. It doesn't scale with the area. So we'll get into that maybe in the next lecture, but we're looking at trying to find a lower bound argument to try to be able to put this system, first of all, to be able to put an abstract system into a highly entangled state that would be, in principle, presumably difficult to simulate. And we're looking at the assumptions that Google's making in terms of how the entanglement's scaling. And so that's the current piece that we're going on. And we just finished kind of looking at how to make quantum computers find matrix product states. And with that, I will open the floor to questions, to insults, to comments, whatever you want. And I will conclude this introduction from, remember, less than an hour and a half ago, you didn't even know potentially what a tensor network was. Now you know how to do matrix product states. And so in some sense, it's very successful. So even though this has been an uncomfortable hour and a half for all of you, it's been worse for me, but you went away with a lot, and now it's time to end. Thank you. Yeah, thank you guys. This happens all the time. No one asks questions, and then right as I go to leave, everyone's like, hey, I got a question. It's like, guys, I just made a jerk out of myself in public on video. It's still going.
Okay, so the last thing which you just explained us is actually ongoing research, right?
Yes, it's ongoing research. So I wanted to end with the current discussion, and we went through a variety of tools from Tensor Networks, and I believe actually, despite the fact that it looks quite easy, I believe if you paid attention to this and you read some notes a little bit and kind of got into Tensor Networks a bit more, you'd pretty much be able to read some papers, like research papers, where they use and they apply this stuff. So.
Can you give a more accurate definition of pi, psi, and phi in your last equations?
Yeah. So okay. So this state will be given as a sequence of operations.
It is operator.
Ah,
We missed 0, 0, 0.
yeah, there's a 0 at the end.
That's,
Sorry.
okay. You have also not only psi, but also phi. What is phi?
No, that's just bad handwriting.
Okay. What is pi sub I hat? What you have I at the left hand side of the equation, but
This thing, or this. Okay.
the
P-
second line.
This is
Yeah.
this is an observable on the ith subscript.
Where is I at the right hand side of equation?
This.
Ah,
Sorry.
it is not comma, it's I.
It's probably look. It's his. It's Yeah, he's right. So there is a little dot here. Okay. And very good. So the question you always ask as a lecturer, because it's always your fault, why is he the only one that noticed this? Everybody else is wrong but one guy. Come on. It's never my fault.
Because he's professional professor from theoretical physics.
Oh, well, that's good. But it's always easier sitting.
Would miss any mistake of you be there next time.
I actually make a tremendously high number of typos when I'm giving presentations. I think more than the next person, but in some sense we make it through. So that was a couple of typos, and yeah.
Okay, more questions?
And you probably missed on the right hand side the letters in the equation for log likelihood, right?
You mean this?
Yeah.
Okay. Yeah, but this isn't my fault. This is theoretical.
Now it will be really perfect. Full blackboard.
Well, okay, so look, the idea is extremely simple, okay? I create this type of scenario, and on quantum mechanics I have to take the square of that, obviously. That thing becomes stationary when it equals 1, right? That's when it's an eigenvector, okay? When you square that, okay, take the modulus. So the idea is very, very simple. It's just a standard technique to take the expected value of an observable. So that's why I didn't focus on it too much. The contribution to this is that you can input a matrix product state of fixed rank, which gives you a fixed rank approximation, and there's a little bit more of abstraction going on in the paper, where you have some kind of feedback loop, and you can play with what Q is. And then you can go into different ideas about what types of Qs should be difficult to simulate on a classical computer and come into different arguments. So it's ongoing work. On the other side so this is the side where it connects to quantum computing more directly. On the other side, you have tensor networks used in theoretical physics, which is ongoing work also at MIPT and other places as well. So.
How many places, by the way, push this?
Okay, so it's actually really interesting. So it's quite popular in Europe. It's very, I would say, not really happened in the United States for some reason yet. Partly because in Europe there was quite a push to do entanglement theory, and this kind of came out of some of those ideas and this connected very well with entanglement theory. Hi, yes.
I have a question about special types of Hamiltonians. You mentioned that we used to work with gapped Hamiltonians, and in this field they always mention only gapped Hamiltonians. Can you explain just very simple why we can work only with gap?
Okay, so for a matrix product state, okay, so the question is this: how long range are your correlations? Okay, matrix product state can only capture correlations that are, I would say, quite local. In the sense, for example, imagine I have a gap system that has a very, very large gap, which means there's a ground state and then a very, very large gap. Okay? Now, imagine I have a system without a gap at all, or imagine I have a system with very, very high range order. Those are very, very different systems. And so there's something called a Mera network, which will correct the entanglement. You'll be able to have an extra logarithmic factor of entanglement on the chains. And we don't only deal with systems that are gapped, but systems that are gapped behave quite nicely because they don't have very long range entanglement. And by gapped, remember, these statements are not well defined. You need to say, what is the gap with respect to? Oh, okay, it scales as some kind of polynomial in the number of bits or whatever it is. So you have to look at the definitions of the theorems. Those are given in the notes that I read. But for the most part, intuitively speaking, if the system does not have a gap, then your matrix product state can still describe it, but not very well. Okay? You would have to have a very large bond dimension. In two
Sorry for interruption. Do you have the same problems with Mera?
Well, it depends. So in 1D, everything's kind of sorted out. In 2D, it's the wild, wild west still. So, and that's why if you're very smart and you want to do kind of a theoretical study at some point, study 2D. Right? 1D is just kind of the warm-up now, but it's still quite useful. 1D is a tool now. I would say that. It's a tool. The research is sort of more solidified. The connection to quantum computing is still new in 1D, but in terms of the systems we can solve. Now, there's other types of networks as well. besides Mera, besides tree tensor networks, there's different, there's different geometries, there's hyperbolic geometries, et cetera, et cetera. So there's a whole huge amount of literature on this. So.
May I use the last question?